bra. You see that the Dirac thing is sort of emerging already. Cat, bra. And it's actually, so this is Dirac, eh? Now you see what I'm doing.
Yeah.
So this is Dirac, this is triangle meets triangle. That's the same thing.
I'm glad you weren't in my talk because I think I was abusing your diagrams.
Okay, and then there are some, this is like some stuff I'm not going to get, but you can then get out of the categorical machinery and sort of obvious assumptions which I was talking about, which there are many more than what I was talking about. You, for example, prove things like that. You can define a scalar multiplication. Scalar multiplication in a picture just means there is a diamond somewhere in the picture. Now, diamonds are not connected to anything with ropes, so they can sort of be moved around. They are not topologically connected by a rope. Like if I would have something like this, if I would have like two boxes connected by a rope, then this rope will always be there. I can move them around like beside each other, but then I will have this rope which is doing something like this. Like these diamonds are not connected to anything, so you can move them around. And basically,
but I mean to some extent, because if you have a tensor product, then it makes a difference where you move the diamond.
what?
If you have a tensor product like V tensor W, S V tensor.
Yeah. No, the reason for that is because of the particular structure of isomorphisms. So when you write down that Hilbert space is isomorphic to Hilbert space tensor, there is a lot of structure in this statement about things you can do with these numbers implicitly. And if you make all this explicit, that's again part of what I said, the obvious assumptions, which are very hard to write down, although because they're so silly that you have to think about them. This then you can prove things like that with it, which formally looks like that. If I've got, you have to look at F and G as a matrix, and as S and T as a number in front of the matrix. You know, you can bring a number inside and outside a matrix. If you multiply all the elements of your matrix with, that's what these numbers mean. That's what this means. This big bullet means putting a number in front of a matrix. And you know how, and this is just a tensor product actually. Putting a number in front of a matrix is a tensor product between this number and that matrix.
So what does the little black for
This is scalar multiplication, I define it here. So this means putting a number in front of a matrix. And then you can bring it in the matrix. And then, for example, if you've got a tensor product of two matrices, then you can bring both numbers out and compose them. Multiplication is just composition of numbers. And so it all works nicely together. This is like very tedious stuff, and to understand the category theory of that, you have to understand what a natural transformation is. And I can assure you, take a book on category theory, you start to read, okay, category, function, functor, natural transformation, then you're already lost. You don't have a clue anymore what things are about. You're sort of gone. I agree. Did anybody do that? Just take McLean, start reading. By the moment you're at natural transformation, you throw it away. you throw it away because you're so lost.
And then you go back and read later that he said that natural transformation was the fundamental notion and that functor was the derivative.
Yes, yes.
But he introduces them.
And then you don't just throw your book again, and then you ritually burn it. Like most mathematicians have done, by the way. Like what most mathematicians have done, whoever came across category theory. But it's just simple, intuitive things. Why did no category theoretician actually ever explain it like this? Why? Because it's just, I don't know what they are. Yeah? Pretentious place. Something like that. So what I'm talking about so far is, for example, so these are two fields where what I'm talking about is like day-to-day business. For many people, like in programming, because they think of these objects as data types and of these morphisms as programs. Proof theory, they think of these objects as propositions and these morphisms as proofs. And now I say practice in physics can think of the morphisms as the objects of physical systems and the morphisms as physical operations. But what I've been talking about applies also to cooking. I can talk about vegetables, meat, fish, spices, mayonnaise, and growing, breeding, catching, cutting, mixing, eating. So this is all the same. So what I'm talking about so far applies to all of this.
Where's the mussel soup?
I've not been saying anything. Basically, I've not been saying anything. So I have to be a little bit more specific about my quantum
The
mechanics.
proof of the pudding is in the eating.
What?
The proof of the pudding is in the eating, so that you can mix it.
Yes.
The proofs in eating.
So the preparation of meat is growing. So there is a morphism which goes from nothing to cow.
Yes.
Or to say mammal. And depending on your procedure, which two sort of animals you start with and you do your stuff, you get either a cow or a pig. So you have to pick out 2 pigs if you want a pig, and 2 cows if you want a cow, and you can't take a cow and a pig, because that doesn't give anything.
Well, unless you're Korea.
Yes.
Chop them all up with a few old stations there.
So, okay, so we're going to be more specific. So we need one particular kind of category to talk about quantum mechanics, because the previous stuff is not going to teach us anything about quantum mechanics specifically. And so there is this concept of Dagger compact category, which was introduced by only in 2004. It's a very simple definition, but it just didn't exist, by Abramsky and myself. Abramsky, computer scientist. So it's very recent, Dagger compact category. So just because people asking immediately, of course, about terminal object, initial object, none of this stuff we want. So you have to do something very different. Cartesian category, no. Because Cartesian category, what does Cartesian category mean? Cartesian category means you always have a diagonal, natural diagonal.
Yeah.
Now, natural diagonal, again, is a very intuitive thing. Natural diagonal means copying. It means I go from type A to A tensor A. I go from one thing to 2 copies of a thing. And I've got a process which does this in a very natural way, in a sort of canonical way. What does naturality mean here? Naturality mean I've got system of type A, I do copying, and then on the 2 components I do something. This should be the same as doing something on the component, on the one thing, and then copying. If your copying operation is just copying and nothing more, then you want this commutation to be true. Yes? Now, in a so this is just naturality. This is another example of a natural transformation, which is very sort of conceptually meaningful. Now, in Hilbert space case, one thing this, for example, implies means basis independence, because you can think of this as unitary exchange of base. So implicitly, by saying this, you already impose basis independence. And as it turned out, you cannot find a map of this kind in Hilbert space which is basis independent. It doesn't exist. And in words, this means there exists no natural diagonal. In quantum computing terms, this means you cannot copy a qubit.